Hello students. So in this particular lecture, we will have a look at the capacitances, different kinds of capacitances associated with the transistor model, and specifically we'll focus on the NMOS transistor model. Get to know the various kind of capacitances associated with the NMOS transistor, and then it will be very similar for the PMOS transistor as well. Right, again, the capacitance is of huge importance because the performance of any circuit design, especially in the digital systems design, it is mostly or heavily dependent on the capacitances associated with it. So in a particular critical path, right, from the input to the output node, if I want the signal to be propagated, it is always, the performance or the delay associated with that particular propagation signal from the input to the output will depend on the capacitances associated with it. And that is where the capacitances extraction of the transistors which are designed for the system becomes very essential. Right, so this is the NMOS transistor model, and I have not taken into account the oxide or the gate. So that is, we will come to that the oxide or the gate capacitances in the later slides. But this one talks about the parasitic capacitances, and then the reason for this parasitic capacitances. Let me get my pointer. So this is the parasitic capacitances, and it is called as a parasitic capacitances because it has been derived from the word parasite. So we really don't want this particular parasitic capacitances in our systems, or we want to minimize this. So if I consider the NMOS transistors, so the bodies of p-type, we have the pockets of n plus and then the n plus on the source and the drain side. So let me use my mouse. So we have this n plus, and then we have this as the p-type. So if I have the body at the ground potential, and then we know that from this VDS, we know that from this particular VDS, the drain is at a positive potential with respect to the body. So this behaves like an N plus, this behaves like an N plus P junction, the diode junction, right? So it behaves like a PN junction diode. And we know that whenever there is a potential difference across it, we will have this, the majority carriers of this N plus drain region, which is nothing but the electrons, which will be attracted towards the positive side. So in fact, this turns out to be a reverse bias PN junction diode. So it is a reverse bias. And we will have at the junction, we will have this, the positive immobile ions. Right, in this case it is an N plus, so it is basically the phosphorus atom which is kind of duped in the silicon material. So I will have this positive immobile phosphorus atoms which are closer to this particular interface of the PN junction diode. Right, on the other side, this is a p-type, so it could be a boron. So we will have the negative immobile boron ions which are formed on the other side of this particular PN junction diode. Now, the reason it forms is because the holes here for the p-type is getting attracted towards the ground potential, and here the majority carriers of the drain, which are nothing but the electrons, getting attracted towards the positive potential, and thereby leaving this immobile ions. Now, this particular immobile ions, as we have seen from the PN junction diode, it forms a capacitance, so they're junction capacitances. Right, so this is one such, the junction capacitances, also called as a depletion barrier, also called as depletion capacitances, and denoted by CdB, where D represents the drain and B represents the body. Right, so this is one particular parasitic capacitances associated with the transistor model. Similarly, on the source side, although the source is at ground potential and the body is also at the ground potential, at room temperature or at thermal equilibrium, we know that in a PN junction diode, the majority carriers will actually flow. The majority carriers will, due to the drift of the majority carriers across the regions of the PN junction diode, we will have the flow of the majority carriers moving in the opposite directions. So if this particular majority carriers in the n plus region, which is nothing but the electrons, will move to the other side, thereby it leaves the positive immobile ion on this particular side, and similarly the holes which will move to the other side, leaving behind the negative immobile ions on the other side. So thereby this forms a depletion barrier or a depletion capacitance. Now it has been denoted as source to body, because this is the source region and this is the body region. Right. Similarly, on the drain to body, we will have CDB. For source to body, it is CSP. So these are the two parasitic capacitances we would like to have a less value. Now this is again a cross-sectional, a little bit tilted. So we will have it kind of a three-dimensional the transistor, and again it is an NMOS transistor. So this is the depletion capacitances or the depletion region that has been formed after applying after applying the voltages. Maybe the voltages of the drain to body is 0, but still there will be a depletion capacitances as denoted by the positive immobile ion and the negative immobile ion here. Right, so I have also mentioned the length of the gate or the length of the channel, which is 2 lambda. Right, so in this case for a 65 nanometer technology node, it will be 50 nanometers, and this remains constant for a given technology node. I've also denoted this LD, which is, don't confuse with this particular L. L is the channel length. Here I have written it as LD, which is nothing but the diffusion length, right? Which is, I have considered it to be a 5 lambda. That is the minimum diffusion length that we can consider for designing our transistors. And then the width of this particular transistor is considered as to be 4 lambda. So this is again a minimum width that we will consider. This D is nothing but the diffusion depth, right? So this is nothing but the diffusion depth. So with respect to this particular dimensions, what we can say is if I increase this LD, the area of the depletion region is going to increase. So what I'm talking about is the area of this region. So a flat surface, so this particular flat surface is what I am talking about. Right, so this particular area is going to increase. So I will just mark it what I'm talking about. And similarly, I will have a similar region around this particular area. With the increase in the LD, this area is going to increase. This will have a directly effect on the CDB. So I will have a larger CDB, right? So I will have this particular area, if it increases, the drain surface, and then the at the body a similar surface at the body side, we will have a increase in the depletion capacitances. If my LD increases, right? If my LD increases, so with respect to this particular point and this particular point, so if I consider the resistances across these 2 points, and if the LD increases, then my resistance also increases. Right, so this is what I have denoted here is the drain. If the LD increases, the resistance, the R diffusion will also increase, and the capacitances here, the CDB also increases. And what we need is actually a lower value. So that's why the LD is actually approximated to a minimum value that is possible. So generally, for most of our design, what we keep is the LD value to be fixed to be 5 lambda. Right, so LD is kept small to keep the R diffusion and CDB value low, and that is standardized to 5 lambda. And the channel length is kept to minimum of 2 lambda for most of our transistor design. So the only one variable which we can change is the width, right? So and also what we have characterized, or in the literature, it has been calibrated that the source to body or the drain to body or the gate capacitances is almost equal to 1 femtofarads per micron of the width, right? Of the width of the transistors, right? So in that case, especially for the 65 nanometer technology or the process node, Using this particular value, we can find out if the W is equal to 4 lambda, which is nothing but, if you remember, lambda is equal to 25 nanometers. And if it is 4 lambda, it turns out to be 100 nanometers. So the depletion or the parasitic capacitances, CSB, CDB, and then the gate capacitances, which we will look into now, will be 0.1 femtofarads. Right, so this has been standardized, approximately standardized to 1 femtofarads per micron. So if it is 100 nanometers, it turns out to be 0.1 femtofarads. Right? As we know that the capacitances CSB, CDB, and CG varies with that of the width of the transistor. Kindly read the expression for the diffusion capacitances, which is nothing but the diffusion capacitance is nothing but the CDB and the CSB. So it is kind of an empirically derived expression that is being given in the textbook, chapter number 2 for the Western Harris textbook. We will now look into the gate capacitances. We will also look into the gate capacitances expression in the next slide. Right. So this is about the gate capacitances. Now the gate capacitances varies with respect to the different mode of the transistors. Right, so if I have a look at the accumulation layer, the accumulation layer, what it means is if the VGS is negative here for an NMOS transistor, if it is negative here, the P-type body, the majority carriers are holes, and then the holes are getting attracted to the interface, and then thereby I will have this electric field which forms the basically nothing but the capacitance, right? So the distance of the two plates, of the two charge carrying plates, will be nothing but the thickness of the oxide, and thereby I will get the capacitances is nothing but, you can also rename it as C0 is equal to epsilon naught oxide WL by T oxide. Right, so where epsilon naught oxide is nothing but K oxide of 3.9 and then the epsilon naught dielectric value. Now the second condition is where the VGS is positive, it is not negative anymore. So if it is positive and it is less than VT, we know that it will enter into the depletion region. So depletion region represents that this positive potential is going to move away the holes, and thereby this particular region is going to be vacant. Right, and thereby my overall parallel plate capacitance thickness is going to increase, because it is not only D value here, the thickness of the oxide, right, the thickness of the oxide, but also some more value where there is a vacancy of any carriers, right? So in that sense, if this overall D value increases, the D means the distance between the parallel plate capacitances is going to increase, and thereby the CGB value, gate to body capacitances, is going to decrease. The third mode is the inversion region. We know that in the inversion region, the gate is at positive potential, and then it's going to move away all the holes, but the minority carriers are able to reach to the interface, and thereby the channel is formed here between the source and the drain. That is what happens in the NMOS as well as the PMOS transistor. So the inversion region, I now have a channel here, and I have a gate here where the charge can be carried, and thereby this forms the capacitances. Right, again, so the thickness of the oxide will determine the distance between the parallel plate capacitor, and thereby which is nothing but the distance between the parallel plate capacitor is nothing but given by the thickness of the oxide. The reason is the charge, the channel is formed very, very close to the interface. So the distance between the two parallel plates, between the gate and the channel that is being formed, is nothing but the T oxide. Right, so my CGB value is now coming back again to epsilon naught oxide WL by T oxide. So in these three different modes, when VGS was negative and when VGS was greater than VT, the capacitances values were same. In between mode, when VGS is from in between the accumulation to the inversion region, that is the depletion region, that is when the capacitance value will be decreased. Right, so in this particular mode, we can also say that the capacitance of the gate to body can also be considered to be a two parallel plate capacitances, where each parallel plate capacitances two parallel plate capacitances where each parallel plate capacitances can be associated with gate to source and gate to drain. Right, so if I consider this to be the gate, right? I can consider a capacitance is here associated with the source point, and a capacitance is here which is associated with the drain point, considering there is a channel that has been connecting the source to drain. Right, again this will be applicable in the linear region. In the saturation region, we will see what is likely to happen, right, later. So in this particular slide, so I'm more focused on the second region where my CGB value is going to decrease, right? So as explained earlier, the overall effective distance between the two parallel plates is going to be more than the T oxide. So especially when VGS is equal to 0, right, it is approximated to, so this particular vacancy is actually very similar to that of the thickness of the oxide, and thereby I will actually get the CGB value to be equal to C oxide or CO divided by 2. So that is nothing but epsilon oxide WL by 2, twice the T oxide. So what it means is the effective distance between the two parallel plates, that is this one, and then wherever it finds the holes, because the holes are kind of moving away from the oxide interface, so wherever it finds the holes, this effective distance turns out to be twice that of the T oxide, right, when VGS is equal to 0 volts. The second condition, when VGS is very close to VT, right, so I've written VT minus, so that means if the VT is 0.3 volts, if it is let's say 0.2 or 0.25 volts, then what is likely to happen? So when it is closer to the VT, it is a depletion region. It is still not an inversion region. It is still a depletion region. So the distance will increase further, right? It is more than that of the 2T oxide which we had seen when VGS is equal to 0 volts. So my CGB value will be actually be lesser than the half of C naught, right, which is nothing but epsilon oxide WL by 2T oxide. So if I want to put it into a graph of the capacitances, the C gate to body capacitances, it will start at a negative voltage. It will start at C0, which is nothing but epsilon naught oxide WL by T oxide, right? It will start from the CO value. At 0, it will be especially half of the CO value, and then very close to VT, it will go down. But once it reaches VT, the inversion region is formed, and then it goes back to the original value here of epsilon naught oxide WL by T oxide. So this value is brought back, right? And this particular value, if I consider, I can also say that this is gate to body or gate to channel. So that's why I've written both the notations. So if I have this gate and I have a channel here, it can also be approximated into, so this will be my source, this will be my drain. So I can also approximate it into two parallel plate capacitances of CGS, gate to source, and then CGD, all right, gate to drain. So if I do that, so this will be half of epsilon naught X WL by T oxide, right? So the graph for the CGS and CGD, only after it forms the channel, that is only after the VT voltage with respect to VGS, I'll get this to be half of C naught. For VDS, so let's say that what happens in the region when VDS grows greater than VGS minus VT, right? So if I consider VDS value, so in the earlier graph we had the capacitance with respect to VGS, right? So in the previous graph, in the previous slide, we had capacitances associated with VGS. In this particular graph, we have capacitances on the y-axis, and on the x-axis we have the VDS value. So we are assuming that the channel has been formed, the inversion region has been formed, and now if I keep on increasing the VDS value starting from 0, what will happen? So once the channel is formed, we know that the CGS value, the CGS and then the CGD value is C naught by 2, right? As the VDS increases, The CGD, right? Remember that as the VDS increases, right? So the VGD, as the VDS increases, the VGD is going to decrease, right? VGS is going to be constant. So what it means is the VGD value is going to decrease. So that means the channel that has been formed at the drain side is going to have an effect, right? As the VDS increases, and at VDS of saturation, the channel drops at the drain side. The channel will be formed at the source side, right? So the carriers, the charge carriers at VDS of saturation, at the drain side will not be there at all. So most of the charge carriers will try to accumulate more at the source side. And thereby we will see this, the capacitance of the gate to the source is actually increasing, and it will go till 2 by 3 C0, whereas the gate to drain, right, from C0 by 2, it will decrease to 0 when it reaches the pinch off or the saturation region. Now the question is, why only 2 by 3 C0, and why not go back, have all the charge carriers, why not have all the capacitances associated with CGS, but why it is only 2 by 3 C0, right, when the saturation region is being formed. So that has been explained here in this Sodini's paper. You can also get it, and I've also uploaded this. You can also get it from the web, or also I have also uploaded it in the reference section. So if I have this as my current equation, IDS is equal to mu W C oxide by the L multiplied by VGS minus VT minus VDS by 2 into VDS. So this is my standard linear equation, right? So if I consider this VGS term and then VDS by 2, it turns out to be nothing but VGS VG minus VD plus VS by 2, right? So this is what it turns out to be. And what we had considered, this particular term VD plus VS by 2 was nothing but coming from the channel, the midpoint, right? The midpoint in the channel, which earlier we had taken. So if I come back, if I consider this to be any point in the channel Y, right, I can rewrite it as V of Y, and my IDS, so the current equation, at any point in the channel, I can actually represent it in the form of Vg minus Vy minus Vt into, if we had this VDS and then there is an L here. So there is an L here and then there is a VDS here. So that has been converted into dV of Y by dy. Right, that's what the Sodini paper says. So the voltage divided by the length, I have actually generalized it into the electric field, right, which is nothing but dV of Y by dy. So this is Y is nothing but any point in the channel, and the dV differential of the voltage with respect to any point in the channel. So this particular equation, the equation number 1, says that I will be able to find out the current at any point in the channel, right, with the help of this particular equation. Now if I consider the charge, right, the total charge is given by the total capacitances multiplied by the total voltage. So don't mix this with V of smaller t, which is nothing but the threshold voltage, right? So this is the capital T. So C oxide WL into, so that will be the total total capacitances multiplied by the total voltage, right? So the total charge here is nothing but WC oxide VT into L, right? So this L I have taken it here. So the total charge can also be written in this particular equation. Just to generalize this, the total charge is nothing but W C ox, right? So VT of L, so what is the total voltage associated? If I take any point in the channel, will be nothing but Vg minus the threshold voltage minus of any point, the voltage at any point in the channel, V of Y into dy. So this Vt into L, right, is actually taken from this generalized expression of the integral, right, where it ranges from 0 to L here, the integral. Right, so I've also represented the cross-section transistor, source and drain, And so it is starting from source side and reaching to the drain side. So at drain, the y is equal to L, at source y is equal to 0, at somewhere in the midpoint, the y is equal to L by 2. And the potential at the point A is nothing but the source potential. Potential at point B is nothing but the drain potential. So going by that particular equation, so I have now two equations, the charge equation and the current equation, right? So if I go back, I have the charge equation here, which has a term dy in the integral. If I go back further, I have the current equation, which has the term dy here. All right, so if I want to substitute this ideas, so in that particular equation, so I can have dy substituted from equation 1 to 2. So dy will come onto the numerator side and ideas will go to the denominator side into this particular equation number 2. So my this equation will be nothing but I will have this square w square c oxide square, and I will have a current, but we are interested in finding out, right, what is the capacitances? What is the capacitances when the transistor reaches the saturation? So I will have the saturation current here, and my integral will be nothing but it becomes dv of v, dv of the point y. So it will be starting from the point A to the point to the drain point, which is Vs and Vd. So if I solve this particular integral, I am likely to get this particular values, right? So Vg minus Vd minus Vds saturation will be nothing but 0. So yeah, let me explain this saturation point. Because we want the capacitances, we want to estimate the capacitances at the saturation point. So this Vd value is nothing but the Vd saturation, right? Vs will be anyways be constant. So I am putting this in Vy, wherever the Vy terms comes, then this will be Vd saturation. And then Vg minus Vt is nothing but if I add and subtract Vs, I'll get Vgs, and then Vds saturation turns out to be 0. This will be Vgs minus Vt, comes outside. So finally, the charge turns out to be 2 by 3 C0 into Vds saturation, right? So considering, the charge here, right, and if I want to find out what is the overall capacitance, so the overall charge actually turns out to be 2 by 3 C0 into Vds saturation. So if I consider, so Q is nothing but the effective capacitances multiplied by the voltage, right? So in this case, if the voltage is nothing but Vgs minus Vt, right? So this effective capacitances turns out to be nothing but 2 by 3 C0, right, at the source side, CGS, right? So this is what we get, 2 by 3. So effectively the charge that is built up, so the charge that has been carried by the channel because of the pinch off region at the drain side, we will get the overall charge to be 2 by 3 C0 into Vds saturation, right? Otherwise, in the linear region, or in the when Vds is equal to 0, we will have it as the total charge is nothing but C0 into Vgs minus Vt. Right here, when it reaches the saturation region, it will be 2 by 3 C0 into Vds saturation, which is nothing but Vgs minus Vt. All right, and that's why we have an effective capacitances to be 2 by 3 C0. The gate capacitances, although we had seen the gate capacitances with respect to the voltage, VGS and VDS, the gate capacitances, VG is equal to C oxide WL. It can also be rewritten as, if I consider C oxide and W together, we'll get C per micron W. So the gate capacitances is nothing but C per micron W. So because W is the only variable in our design parameters, because the L and other parameters, the channel length and the other parameters, even the LD for the diffusion regions, diffusion pockets are constants. Only thing that is variable is W. So we can also consider it to be the C per micron into W, and where C per micron is C oxide into L, where L is the technology node dependent. So C per micron for 65 nanometer is roughly 1 femtofarads per micron. So based on the W, we will have the different the gate capacitances. So for a W of 100 nanometers, we can see that CG turns out to be 0.1 femtofarads. So that's what we had seen in the previous slide also.